Okay, so we're going to talk about the excuse me, we're going to talk about the concepts behind doing a large sample confidence interval for a population proportion. So a confidence interval for a population characteristic is an interval of plausible values for the characteristic. So when we go back to the last section, we were talking about point estimates. We use that point estimate as kind of a center for our data. And then we say, okay, well, based off of that, what would a normal distribution look like? And then from that normal distribution, we try to determine things about that sample that we took to see if it in fact makes sense based on other data that we understand. But basically, an interval, again, is a lower bound and an upper bound. And we're trying to capture a certain area of data. So like, how confident do we want to be? Normally, if you're confident about something, you're going to not only go to the left, but also to the right, a certain number to be confident, especially if you're in a symmetric distribution. So it's all about trying to capture a percentage of times and have it the smallest interval that you can in order to say something about a proportion or a mean, which we'll talk about later. And so we use our point estimate as the center of that, and then we spread out to the left and right, or to the lower and above, in order to try to capture the largest amount of area or that we want with the smallest range. You'll see the term confidence level. That is basically the success rate for our confidence interval, or the percentage of area that it captures. The numbers that you'll see most often will be like 90%, 95%, 99%, and so on. When we're talking about population proportions, so we have, you first set up, you get a p hat. And p hat is kind of our point estimate of our proportion. So whatever our study or our data suggests, and we find the number of successes over the number of trials, and then that tells us what our mean is. And then we're going to use a standard deviation right here, which is what we've learned before, is the square root of p times 1 minus p over n. Now, this is a little bit more accurately what it might look like. We're trying to, so if we're trying to find, let's say, to be 95% certain of something, we're going to look, at our point estimate, which is going to be in the middle, which is p hat, and then we're going to try to encapsulate 95% of the area around that number. So you're going to see common z-scores used. For 95%, they have z-scores of 1.96 and negative 1.96. Those are like your lower and upper bounds for the z-scores. Now, we'll have actual numbers later on, but 1.96 standard deviations above the mean, all the way down to negative 1.96 standard deviations, so 1.96 standard deviations below the mean, that is going to give us 95% of the area. So you'll see this quite often. Now, if you have an n that's large enough, approximately 95% of all samples of a certain size, so of the sampling distributions that we've studied, so 95% of those sampling distributions will result in a p hat value, or your sample proportion, being within 1.96 standard deviations of your mean. So what does this look like? So let's say this is the sampling distribution of p, of our statistic, of our proportion that we're finding. This is it. Okay. Now at the center of this is our true proportion. Okay, that's the true proportion. Now, our p hat is very rarely going to be that exact number. Okay, very rarely. And so when we create our interval based off of those things, you'll see that, if p hat, what if p hat's a little bit smaller than our mean? So a little bit smaller than our true proportion. Well, its interval is going to be created, and it's going to be contained in that number. That most of the time is going to happen. But very rarely, you will have a p hat that falls outside of that, right? You see that the chance that we get a p hat that's this far outside or this far away from the mean is very, very small. It's very, most of the time you're going to get it right from here. But what if it's not? That can still happen, and you'll have a confidence interval that's way out. But the chance that that occurs is very, very, very small. And this is going to come into later when we're talking about our hypothesis testing, is that since 95% of our sampling proportions are going to come in this area, we can be 95% sure, if we know the true proportion of what we can expect from one of these things. And it's very important to say what we could expect. Now, you can always end up with other things occurring or other outside shots happening, like this one over here, where it's really far out of the way. But that doesn't happen very often. And in fact, you'll see it only happen about 5% of the time, which 95% is fairly confident that what we're going to see. So if you're trying to build this interval, the way that it works is pretty easy. A lot of this math may look very complicated, but it's not too bad. At the center, you have p. It's very similar to the quadratic formula in a sense, if you've worked with that you're going to have a center of p, or p hat. And to the left, you're going to be subtracting 1.96 standard deviations. So you're going 1.96 standard deviations away, going down, and you're going forward 1.96 standard deviations. And that is what your interval is. It's what's this point and what's this point. That's what the interval is. That's what all of this stands for. And 1.96, again, is the z-score associated with the middle 95%. So that's where that 1.96 comes from. Now, along with this, we can create that interval, but we need to have three things happen. The first thing we've studied is that our sample size times our sample proportion, and our sample size times the complement of our sample proportion have to be greater than or equal to 10. That needs to occur in order for us to be sure about this. The second thing is that our sample size needs to be less than 10% of the population without replacement. So generally, you're going to have to make some sort of assumption based off of the context of the study, that the data that we have is less than 10% of the entire population that we can take from. And then also you need to know that the sample can be regarded as a random sample, so that it was selected from a random group, whatever our population is. Whatever population you're considering, the sample needs to be taken randomly in order for this to be used and to be as accurate as possible. Now, you don't just have to do this for 95%. It can be done for any type of confidence interval. And the formula is basically the same. The only number that changes is whatever your z critical value is. For 95%, we use 1.96. But if, let's say, we wanted to do 90%, that number is 1.645. And if we wanted to use 99%, then we're going to use 2.58 as the z-score, which goes right here. Now, these numbers can be taken care of automatically by using our calculator, but they're good ones to remember for the future as well. So if you do have time to associate, these percentages with these z-scores, to write those down, that would be excellent. Now, last couple things about this section. You'll hear the term standard error. Standard error is the same thing as when we're using a statistic to estimate standard deviation. So that's just the estimate of it. We're not totally sure it's the standard deviation, but it's an estimate. And then you'll also see what's called bound on error of estimation. So that's what this B, capital B, stands for. So that's basically how far to the right and how far to the left of our mean are we using to capture. Um, so if we had a mean, if we had our mean, it's our P hat here. B is going to represent exactly how far we go in either direction. That's what that is. So it's how far do we extend one way or the other in order to figure this out. So this can be very, very helpful when we're trying to determine a sample size. What if we want a sample size, or what if we want a certain bound on error? We only want to be this far off on our guess. Now, we can use math to help us determine exactly the sample size that we're going to need to make a standard deviation small enough to make this happen. And that's this formula right here. So if we were looking for a sample size, n, based on a certain bound, what you do is you do p, which is your probability, times 1 minus p, times whatever your z-score is, which again, we're using 1.96 a lot because this is associated with 95%. So we use our z-score over our bound, which is that left and right movement, squared. So all these formulas you have, but you're going to need to know this for certain types of problems that we have when you're searching for a particular sample size based on a particular bound, this B that you're looking for. The last thing that you have is, let's say that they don't tell you what your proportion is. So you're just trying to guess. Well, we use a conservative number, which is P equals 0.5. So basically a 50% chance. If we don't know the probability of something, we're going to use a 50% chance, because what that is going to do is that's going to give us the highest sample size that we would need, that you could possibly have given your proportions. So like a reason for that, so look at this section here, P times 1 minus P. If you did 0.5 times 1 minus 0.5, that makes 0.25. Okay, well, it's very, very small. It's a small number. Now, if you were to pick any other numbers, okay, so like if you said 0.7, and let's say 1 minus 0.7, so the further you get away, this ends up being 0.21, which is a smaller number. So we're going to get a smaller sample size here for that, because this number here is smaller. If that's smaller, then the n is going to be smaller. And if we don't know our proportion, we want to just assume to make something a very conservative guess, give ourselves the largest sample size, just so that we know we can be very confident that all our data is working. So basically, this is just in case they don't give you the information, you're gonna say, okay, we're gonna just go ahead and call P 0.5 or 50%.